Everyone's talking about language models. So am I. But let's take a step back. Let's look at the cutest photo that you're ever going to see. This was taken about 30 years ago. This is the 95 version of me. This is my sister Tash, and it's powered by very fancy neuromorphic technology. This sub-threshold nuts. It's a cassette. It's very dumb. But yeah, this was a Christmas gift to my sister from my parents, and she gives me the robot. And I was hella excited about it, right? I took the robot, I ran away with it, and my sister was like, yo, it doesn't cost you anything to say thank you. Now, I'm a very patient person. I'm very pleased to announce that 30 years later, Sam Altman has verified that it indeed does cost you a little bit to say thank you. So with that being said, LLMs, expensive. One of the goals of my lab is to take these ridiculously expensive workloads and try to make them a little bit cheaper. That all the SNN torch hype in the chat, that's so funny. Okay, so let's try to abstract language models into their constituent components. You got token mixing. That is, you take a bunch of information over a sequence over time, and you, I guess, mix them. You try to make sense of information over time. You got channel mixing. In the language modeling context, these are often just a ton of feed-forward layers, and I guess these channel mixers are trying to take your inputs and see what information they're relevant to. So you can kind of think of the entire internet being compressed into your channel mixer. Maybe you like to visualize it as a lookup table of fact storage and whatnot. There's also normalization and residual streams, and these two things really just serve the purpose of, I don't know, making gradients flow effectively. You take these, you repeat them, you stack them, you repeat them way too many times, bam, language model. So with that being said, I want to give you a vibe on what a token mixer looks like. So let's take this silly sentence. Shrek saw Taylor with binoculars. Right? Shrek saw Taylor with binoculars. So my question to you is, who has the binoculars? Is it Shrek? Is it Taylor? Linguistically speaking, this is ambiguous, right? But because we have brains, because we have a bit of context, we can probably appreciate that Shrek's our man. Shrek's the hero with the binoculars with whatever nefarious purposes. But if we're going to feed this into a language model, every single one of these words is represented by a vector. They get fed into this channel mixer, token mixer setup again and again. Eventually, somewhere in your model, you're going to be generating what's called an attention matrix. The idea of this attention matrix is to basically find which of these words are correlated to the same words, right? So in this silly example, maybe the number that represents the link between Shrek and binoculars lights up, right? Denoted by this deep red. In that instance, yeah, self-attention, the transformer mechanism behind language models, has figured out that indeed Shrek and binoculars are tightly related. The catch here is that if I want to add an extra word, then I'm going to need an extra vector along the x dimension. I'm going to need an extra row along the y dimension, so you can kind of see this potential risk of n squared quadratic scaling. So it does grow quadratically, but in contrast, your brains aren't undergoing neurogenesis with every word I say, right? Like you have perfect memory in a way. You're storing every sequence element, but brains are a bit more efficient. I don't think I really need to preach to the choir about this, but why not just swap out our token mixer, go from this attention mechanism over to, I don't know, a recurrent neuron or a spiking neuron. Now, truth be told, it's kind of gone the other way. Like back a decade ago, people were looking at how to use sequence models to do, I don't know, basic language tasks. But it was hard, right? There's a lot of problems with recurrence. And so people moved to transformers, partially because they work so well, partially because they leverage the parallelism of GPUs. Whereas you're kind of stuck with some sequence models, sequence-based processing with considerable time complexity when you move to recurrence. But in either case, let's look at this. Let's look at token mixing. Let's look at my own lab's trials and failures and successes of how we've gone with trying to take neuromorphic principles into LLMs. But naively, the reason that we might not want to do this could be something like this. If I take this leaky integrate and fire neuron trace, maybe this first spike represents the token Shrek. And by the time you've reached binoculars, all that juicy information about Shrek, didn't think I'd say juicy and Shrek in the same sentence in this talk, but all of that information has faded, right? So the problem there is that you've got this kind of very localized memory. Uh, the gain, of course, is that you're not expanding that memory with time during inference, right? During inference. So that one neuron has one state. It doesn't increase the number of states that it has. So memory no longer grows with sequence length, but your performance is going to degrade as a result of all of this. And so by the time you've reached that final token of binoculars, you run this risk that all information, all context about Shrek has disappeared and been superseded by Taylor. So I don't know. Despite all that, despite all the shortcomings, we were like, let's just see what happens if we take a spiking network, smush it with language, and see what happens. And this project was sponsored by Intel and stuff. Yeah, okay, so we've moved away from the Jennifer Aniston neuron and over to Shrek neurons. So SpikeGPT, at the time, it mattered. And I'm only bringing this up because I think it's at least good to set a bit of foundation on where we went from, the lessons that we took from this model. But Rujia built this out. It was the largest spiking neural net trained via backprop. So this was all at the time when we dropped it in early 2023. And it was the first of its kind to perform language generation. We had 3 variants across a few different parameter sizes. And of course, you should be able to catch that this is around 10,000x smaller than your trillion parameter models now. So it's very much a toy model. I'm embarrassed of these performance samples. They were cool once upon a time. Let's not worry about it now. But what are the points here? So, you have recurrent dynamics. We do have slightly more complex internal neuronal dynamics on top of the leaky integrate and fire neuron. They are in there, but this is based on the Rock-Hoof model. With leaky integrate and fire neurons that precede every single dense operation. So the point is that any, I guess, n-squared complexity operation is going to effectively be sparse. So that was the point. One other thing that caused this to work, that let us scale to a point, was the idea of data-dependent decay. I'm going to bring that up a little bit later. But intuitively, if you're coding in SNN torch, and if you are, I'm so sorry, but if you are, then you often hard code your decay rate, or you might set it to be learnable. But the way that the, I guess, state space model and recurrent community have kind of gone are making that decay rate a function of your input. LSTMs and GRUs do that as well. And that really helps. Overall, yeah, sick. 30x less operations than a transformer of equal size. Why isn't the world using it then? Let's be honest with ourselves. Scaling really hurt. And we were very transparent in the paper about this. We tried to go up to 1 billion parameters. SpikeGPT is the king of hallucinations. I'm just psyched that it generates language, to be honest. So why isn't the world using it? So scaling really does hurt. We tried to train a 1 billion parameter model, so 4x the largest parameter size here. And the performance improvement we got was effectively negligible. There really wasn't much of a scaling war to be observed. So yeah, let's be real, the model is pretty dumb. I guess that's still neuromorphic. Humans can be pretty dumb. So yeah, we're very, very brain inspired. If I had to be honest, my honest take on why I think this didn't work that we're struggling to make this work is probably just it's not non-differentiability of spikes. I really think that's been solved by, I don't know, people in this call. I really think it's just binarized activations not being used effectively. Those are damn hard to work with. It's excessive information compression. No ablations run, but I'm pretty confident that that's the reason. So all of that is to say, if I was to just naively train a spiking neural net for language generation, then I'm going to end up with something like this. This is by far the dumbest slide I've ever put together. I'm very proud of it. So we perhaps don't want to do that, but we do have this world where, okay, attention and transformers are powerful, but damn, they're pretty expensive. Spiking neural nets and perhaps recurrence more generally, they are cheap, but based on the information I've given you so far, they are quite weak, right? So if we were to push towards using SNNs as an alternative to self-attention, and I'm going to start generalizing a little bit. I'm going to go from spiking neural nets to just recurrence more generally. The key challenges that we face are backprop through time, reliance on an operation that follows cubic complexity, and poor long-range performance, right? Actually, this vector matrix should probably say matrix matrix. So let's address these iteratively. We're going to look into state space models. Of course, I need to shout out Chris Elias-Smith's work from 2017, 2018 on LMUs. But the idea is that, we've probably seen some variant of this state space equation before, where x is your hidden state, a and b are coefficients. The rate of change of x is dependent on x itself. And when you see something like that, you expect some sort of exponential relaxation. If I was to go ahead and solve this equation through a bunch of sequence steps that, I don't know, belong in the appendix of a paper, then we end up with this discrete time solution. Given that we're at a spiking neural net conference, I think that this should really look familiar to everyone, right? RNN's not too dissimilar, right? The key difference that I want to highlight just for now is that you're applying a nonlinearity to your hidden state through time. Is that a problem? Well, let's see. So this discrete time solution is recursive, and assuming that alpha is between 0 and 1, forgive me, in SNN Torch, my naming convention was to set the decay rate as beta, so I'm just catfishing everyone on this. Let's say that we've got an input, we've got x1, x0, x2, and I put them out of order because different neurons can spike whenever they want. Each of these spikes is going to elicit its own exponential relaxation kind of looking thing. That's fine. What can we do with that? If I was to code this up in SNN Torch, then we see some cute animation like this. Point is, you construct your network, and then I need to run this in a for loop. I need to increment through every sample of data one at a time. The next time step is a function of the previous time step. So inference, training give you linear complexity, memory, and computational with time, right? We want to break that. Why do we want to break that? Because if we're stuck with training on data, on the internet scope of data, then we can't afford to wait for one token after another token. We really need to parallelize this to reach tractable amounts of time, right? So what can we do about that? Well, it turns out that if you have a linear time recursive equation, then you can pull out a closed form solution, right? And this is kind of obvious. Like, we know that the solution to one of these inputs is going to be an exponential function. And you can literally see it, right? X1 generates one exponential decay, X0 generates another exponential decay. And so this can be implemented very efficiently using a 1D convolution or whatever scan that you prefer. The idea is simple, right? You have many streaming processes on your GPU. X1 might be allocated to one of them, X0 will be allocated to another one. And these cores are going to be solving the independent response, the independent exponential as a result of each of these inputs. And then once you've got all of these three kernels, sum them together. And if you have more inputs, then of course you're going to utilize more of your cores on your GPU. Of course, this assumes a linear time equation. So if we want this to hold true in the spiking neural network world, you need to eliminate your reset in the way that I've kind of posited it to you. Otherwise, that reset is going to add a nonlinearity because the reset is a function of a spike. That spike is a function of a heavy side, which is thoroughly nonlinear, right? So that's kind of a win, right? It's not something you can do with recurrent neural networks naively. And actually, just as literally less than a week ago, we probably did the biggest change to SNN Torch in 3-4 years. So we introduced the state leaky neuron. It's not documented properly yet. I think you've got to go to an obscure tutorial that hasn't made its way to the website, and it's not even on pip yet. So you've got to install SNN Torch from the GitHub source. But the point here is that I can take my stream of data that's varying over time and generate a stream of spikes, a stream of states, a stream of membrane potentials, all in that one parallel hit. So that is enabling much, much, much faster training as a result. And I don't know, hopefully that's useful to someone. Cool. Point is, backprop through time, tick. I feel like that's probably the best that we can do from the recursive side of things. there is still this reliance on matrix-matrix multiplication, which leads to cubic complexity. Let's break it down a little bit. Let's take a vanilla recurrent neural network and say we've got our hidden state X, which equals a transition matrix. I've neglected the nonlinearity for now. That's multiplied by your previous state, denoted by this subscript 0, with some input. Cool. Let's vectorize our notation, and let's increment to the next step. So we're getting current time hidden state, next time hidden state. Let's now do a substitution. If I was to expand this out, I'm going to end up with a w squared term. And all that really matters here, don't worry about the math. What really matters is that every increment, if x2 becomes x3, then I'm going to get a w cubed term. And so matrix-matrix multiplication here is going to follow cubic complexity. You can play a bunch of tricks to drop that to like, I don't know, 2.38, but those are in very corner cases, still expensive. What can we do about that? If we look at the spiking neural nets and element-wise linear RNNs, we're not doing a matrix vector multiplication there. The transition is just, every neuron has its own independent decay rate. So this element-wise product is denoted by this circle with a dot in it. I'm going to bring back that vectorized notation, replacing everything with the element-wise operator. And in this case, if I square this vector, W1 gets squared, W2 gets squared, all of these things get squared independently of each other, and that's a very cheap operation. It scales linearly with every additional neuron that you have. That's nice, but the obvious challenge here is, are you losing a bunch of your representational capability? Well, hopefully I can convince you that's not necessarily the case. And this starts to come from a lot of literature in the state space model world. But let's say that we have a square matrix. You diagonalize it using your favorite, I don't know, diagonalization technique, eigenvalue decomposition, or whatever. D is your diagonal matrix. We'll bring back those hidden state equations, recognizing that W squared is the pain point. If we were to expand out W squared, we substitute it in for PDP inverse. You can hopefully see where this is going. That disappears into your identity, and you're left with PD squared, P inverse. And if I increment to W to the 3, the only thing that changes is that D term. Raising D to any index is just going to follow linear time complexity. It's equivalent to element-wise operators. I think that's kind of beautiful because, I don't know, the spiking neural net community were already doing this for a very long time, but we didn't necessarily realize just how valuable it was. And it was the language modeling, state space modeling community that pulled this out and prescribed some theory to it. Of course, taking the inverse of a matrix is kind of expensive. You could pre-compute it, or you could do what the deep learning people did and say, let's just make it a different learnable matrix. We break the equivalence, but if you make more things learnable, you have more capacity to learn. So, I don't know, bit of a hack. Another thing is that if D here, so D is the only thing that changes with time. So you can kind of visualize P and Q to be linear layers. Of course, you can add nonlinearities to them to address the universal function approximation problem, right? But D squared is the only thing that's changing. So you can kind of think of it as a linear, recurrent, linear layer stacked together. If your eigenvalues are between 0 and 1, then you're going to have static decay. That's just your beta. That's your decay rate, or alpha in the previous slide. If you use complex eigenvalues, you get oscillations. And this has a bit of potential because you're effectively bringing information back from the dead in a way. That's kind of cool. Address that problem. Happy days. Now on to poor long-range performance. That's really the reason why people moved away from recurrence. So one issue with RNNs is that they are nonlinear through time. If I bring up the sigmoid or tan H looking function, we take the derivative of it as your hidden state tends out across either extreme of your x-axis, then your gradients vanish. But by linearizing my recurrent equation, which we already do in spiking neurons, you buy back a little bit of that, buy back a little bit of your vanishing gradient issue. You can also use complex value transition matrices. So I've just brought up oscillatory decay. And for those of you that are familiar with language modeling, the current way to do positional embeddings is some variants of rotary positional embeddings, which is basically oscillations. So if we want to look a little bit more like language models, then we could start considering using complex value decay rates. The thing that I think helps the most in long-term dynamics with recurrent neurons is making your your decay rate a function of your input data. So that has really helped. We did that in SpikeGPT, and we've done this in the next model that I'm about to show you. But effectively, all of these things were addressed. We rolled together all of these ideas that I just explained to you into a model, into the MatMul-free model. Before I go there, I want to just give you a high-level overview of where the state space literature has gone. So I like to call this generation one, just your gated vector recurrence. This could be element-wise linear products. So this is effectively what spiking neurons do, right? Hopefully this is a very familiar equation, just with different notation. Gen 2 started taking outer products, so you're operating on matrix-valued hidden states. The reason that people went there was because, so you lose locality. Every neuron no longer has its own independent decay rate. But the reason the community went there was because GPUs have many cores and they need to utilize those cores. I mean, the GPUs are being powered regardless. So it's a waste of money if you're just going to overpower them and only run very simple operations. So that community has gone towards Gen 2 and Gen 3. Gen 3 gets a little bit more finicky. If you do want to go into more detail, then I'll show some references on where you can learn a bit more about this. But yeah, we took these ideas. The MatMul-free language model is it classifies in the Gen 1 case. So it bears a lot of similarities to spiking neurons without actually using spiking activations. We use ternary parameters instead. A lot of what we learned about extreme low precision was snowballed into this model. So you get pretty good memory. The learning to forget idea that comes from LSTMs is just data-dependent decay. Your decay rate is just determining what should we forget. And that is really important, right? If you're not expanding your state, then you need to forget something, right? If you're not going to expand the memory usage with your sequence length, then you need to learn what information is no longer useful to you. So LSTMs did it, and there is an incredible amount of value in porting all of that to these linear recurrent systems. And for those of you that are like, oh, what's a state space model? Yeah, it's just a recurrent neuron with a linearity, with that it is linear through time. So linear recurrent networks are what we're talking about here. And we've continued to optimize since publishing or uploading the preprint, and we're hitting 2 watts at human readable throughput. So I think that's kind of nice, and it's at the billion parameter scale. High-level diagram, which is the blocks that are compiled. It was a very non-trivial effort to map this onto Loihi or Loihi 2. And we've optimized it for a couple of workloads, right? In transformers, you have prefill and you have auto-regression. Prefill is the phase of language modeling where you have a long sequence, like you've typed into ChatGPT and you hit enter. So given a long stream of words, let's find the next word or token. Auto-regression or decoding is, so we've already done prefill. Now our task is to find the second word and the third word given just one new word of information. So with prefill, you're actively utilizing all of your Loihi chips, and auto-regression, a lot of these are off. So there is a potential advantage here because given an asynchronous chip, you don't need to waste energy on a clock on chips that don't have any words being streamed through them. Whereas prefill, yeah, your pipeline is totally full. If that doesn't mean anything to you, don't worry about it. We'll look at some of the results here, where on the x-axis, we've got the sequence length. We're increasing that out, and 1024 is pretty small now. On the y-axis, you have throughput in terms of samples per second. How many words, how many tokens can I generate in 1 second? And higher is better. And this blue line is the MatMul-free model. These other 3 are the Transformer++ baselines, which are the backbone of all your open source LLMs, Llama, and QN, etc. Truth be told, we're not doing great to start with, but eventually we start winning in sequence length regimes where that really matter at scale. But it's still not great, right? And the thing that we're not capturing here is energy efficiency. So I'm going to show you one of the cheesiest plots that I've put together ever. On the x-axis, we have joules per token. How much energy does it cost for 1 token to be generated? Lower is better, so we want to be somewhere here. On the y-axis, we still have throughput normalized to 1 watt. How many words can I generate per second given 1 watt of power? Higher is better. We want low energy with high throughput. And these green circles indicate the 1.3 billion parameter and 2.7 billion parameter transformer plus variants. So we're going to get super cheesy. I'm going to zoom out in my VC pitch deck, and bam, this is where MatMul-free sits. It's right where we want it to be. But these are ternary models, right? And so they're still using less memory than the Transformer 16-bit BrainFloat 16 whatever parameter models, even though they're parameter matched. And so you're effectively getting far more using far less. In terms of performance on short context benchmarks, we basically matched Transformer++ on everything. Long context is when state space models start to get weaker. But there is more to say about that. That was awesome. It was nice to start getting a bit of viral traction. We did have this point where where we were achieving a cool amount using very limited GPU resources, and as a result of that, a few places hit us up and were like, "Hey, we have more GPUs. Can you do cooler things if you were to scale this up?" So one of them, I'm going to show you two things. As I understand it, there was one talk that didn't happen, and so I'm going to milk it and go slightly over time. But aiming for state of the art was kind of the next thing that we looked at, not just efficiency, but again, we're still taking so many lessons from the spiking neural network world. We started looking at hybrid models, and it's very simple conceptually. Just take a bunch of your state space layers. This could be MatMul-free variants. It could be I don't know, your linear recurrent neurons. These are all the same thing. You repeat them n times, and every now and then you throw in a full attention layer just to boost back that long context performance, right? So we did a pretty rigorous study on this. These two plots are basically showing, I guess, accuracy, like the score of your language model. On the left, short context benchmarks. On the right, long context benchmarks. The dashed line is the transformer, just a pure transformer. So that's really what we want to beat. On the x-axis for both, on the left side, we're saying we have, so 3-to-1 indicates 3 state space layers, 3 linear recurrent layers for every 1 transformer layer. 24-to-1 means that you have far fewer transformer layers, and then pure is just a pure state space model. So the takeaways here are that short context benchmarks, transformers don't seem to bring any value. So you're just paying a huge memory cost for not much. But on long context benchmarks, that's what is a bit harder to beat with these linear recurrent models. So something's got to give. But if we look to hybrid models, then in this 3-to-1, 6-to-1 ratio, you do see a few of these hybrid models matching. And you're using something a lot cheaper than just a full transformer. Another finding that was quite interesting was that the best solo state space model, SSM, doesn't guarantee the best hybrid model. So yeah, we trained a ton of models to pull these results out. And what was really validating was seeing QN3, Alibaba's model, doing this at the industrial scale. So this is a hybrid model with, I believe, a 3-to-1 ratio at the 80 billion parameter scale, and it works really damn well and is pretty damn cheap. So this was only dropped within the past month or so, I think. And this uses the Gen 3, if you recall the timeline of state space models. So yeah, this seems to be that all the state space model literature started from the neuromorphic world, from the spiking neural network world, and we're really seeing it kind of working in practice and at scales that I honestly blow my mind, man. That was the first part of our SOTA chase, right? The second, and this is, it feels kind of cheap though, right? You're just taking state space models and then a transformer, and you're not really integrating them effectively. Like it just feels like deep learning hacks. And to be fair, a lot of deep learning is just hacks. But yeah, if you want to reach the best model ever, then you do have to succumb to that to some extent. But we try to merge these a little bit better, which leads me to a paper that we literally dropped within the past week as well. So it's been a busy week. I'm very tired. But imagine you apply recurrence to a transformer. That's where we're going to go here. So OpenAI dropped their scaling law concept back in 2020. Hopefully we're somewhat familiar. If you're not, very quickly, all they said was that model get bigger, loss go down. Oh, but also if model go bigger, data set need to go bigger as well. So these two things need to commensurately sort of decrease together. And ultimately, if you combine them, more data means more compute, a larger model means more compute. So you can effectively project, you can figure out the budget of GPUs that you need for a given loss. Now, this paper is somewhat outdated. People have come up with alternative scaling laws. But with that being said, my question to you is, what is the limiting factor between dataset, parameters, GPUs? Now, it turns out to be the dataset. We've already exhausted in the deep learning LLM world. They've exhausted the internet, right? Everything from now is just GPT slop. But there's only so much data that you can use, and so that kind of sets an upper bound on how much useful compute you can throw at LLMs to improve their performance. So the question we're now asking is there a way to decouple your data set from your compute, right? Reasoning models were the obvious answer here. Hopefully we're familiar with the idea of thinking models when we use ChatGPT to write our research papers. Don't do that. Let me give you a sense of what reasoning models are doing, though. Let's take this math equation and generate a response. Let's generate multiple responses, right? One of these is correct, 12. And so reasoning models reward during training, your model needs to already have a sense of a correct answer. And when you undergo reinforcement learning and chain of thought and unroll all of this, it's sort of amplifying that correct answer. Let's do a rollout. Let's see how it arrived at that answer. Okay, so yeah, you iterate over the sixes. And so the problems with this are, one, you're extending your context to arrive at the final answer. Two, pre-trained models still need at least one correct answer, right? You apply reasoning to a model that has learned to predict the next most likely token. What can we do to increase the chances of getting that correct answer before reasoning? You got to increase your model size, your data set size, but we've kind of hit a limit there. So there's a bit of a catch-22. Reasoning models are really limited by data sets as well, right? And finally, you are operating on your vocabulary. In chain of thought, you're taking the output token and feeding that back into your model to iterate. And a lot of concepts are a lot more abstract than that, right? So I feel like there is something more to be said about reasoning in the latent space. And so that is effectively what we did with this next model. And so Ridger is the hero that really led the charge on this. And I guess Yoshua Bengio found the work cool enough to jump in. So we just dropped this paper very recently, Scaling Latent Reasoning via Looped Language Models. We've released the models. They work. They are currently SOTA, which is kind of weird to me, just being some dumbass from the most isolated city in the world in Perth, Australia, moved to Cali. The idea is basically you take the latent space output, you pass it through an exit gate, say, is the model confident enough to use this, or should we keep looping? Should we keep operating? You loop R times. Eventually, your exit gate shows enough confidence in your model, and then spits out the token, and you go to your next token. So it effectively gives you a third scaling dimension for pre-training, right? Because reasoning is a post hoc thought. Reasoning is applied to pre-trained models, but here I'm saying that now you can pre-train not only with data set and parameter size, but you can bake in latent reasoning into the pre-training process and take advantage of the trillions of tokens that are available to you there. Your data loops through the model. There's this dynamic termination idea, which we know ChatGPT and whatnot have some variant of. It's just a black box to us. So I guess this is open sourced. It operates on the latent space, and this isn't a wholly new concept. The universal transformer did something very similar, but at a tiny scale. So we did take a risk when we suddenly found ourselves with 1,000 GPUs to burn through. It is the first looped model to be trained at this scale, 7.7 trillion tokens, which is cool. And as a result of that, we were on par or beat a ton of other models that are larger than us. The things to pay attention to are our model, 2.6 billion parameters, and Aura is the name of the model, after Ouroboros, that little infinite loop cute thing. So red is where we are, and this is our 2.6 billion parameter model. It's on par with QN3, the 8 billion parameter model, and Gemma 3 from Google, which is 12 billion parameters. So the fact that you are doing more computation. You're not doing more computation. You're basically doing the same or less computation as these larger models, but we are using far less memory in our 2.6 billion parameters. So the thought process really is, to reach SOTA, you need more parameter efficiency. You want to use what you have far more effectively. And I think that's what we've really done here. I'm not going to go through this, but I just want to make you aware that training LLMs is a pain in the ass. There are a lot of different phases to it. It's a very engineering focused field combined with a bit of theory, which made me a little bit scared of going down this road. but we've listed out all of the steps. It's all very transparent. We even tell you how much the shift in data, and we increase the quality of data as we go through the training pipeline. So it's pretty cool. But the main takeaway here is that combining recurrence and transformers, all this recurrence that I wouldn't have stumbled upon had I not been, I don't know, exposed to Dan's work on SNNs and Freedom and Spike Torch that ultimately led to SNN Torch. All of that enable very cute models, 2 billion parameter models, to hit the level of frontier 8 to 12 billion LLMs. I think that's really cool I do have to say that this was a very collaborative effort. No chance in hell I could have done this solely on my own, even Richard himself. We do have to thank a lot of other places, so ByteDance, Contium, and a few others for helping us with getting those GPUs. So, damn, some takeaways where we're nearly there. Forgive me for going over time. Lessons for spiking neural nets. SNNs were already doing what linear RNNs were doing, right? Element-wise recurrence and those kind of local operations. But in the deep learning context, my take, and this is opinionated, I feel like they're only going to be competitive if we make them linear over time. So that makes you want, do you really need to remove that reset mechanism? I think so, right? Secondly, if you want to hit that top performance with your SNN, then you should be looking at the state space model literature. There's just so much more money, so many more bodies and brains that are targeting that area right now. And so it makes a lot of sense to leverage some of that research. Low precision, exact same rationale. The language modeling community has done an incredible job in a short amount of time. I mean, granted, there's so many people and again, so much money, that if we want to figure out how to use binarized activations to our advantage, we should probably look at what they're doing as well. But that's not to say that there's just things for SNNs to learn. The deep learning community should be learning something from us as well. Recurrence is key. I think recurrence has really unlocked state of the art, and reasoning has proven that. Hybrid models of all sorts are currently winning. Loops at that single billion parameter regime, and then the hybrid SSM transformer case as well. And sparsity matters. If we want to hit those really sweet energy numbers, then we need hardware that can take advantage of it all. And I think that low-EHE MatMul-free implementation definitively proves that. So none of this work is possible without the absolute stars in my lab. In this case, Ridger has led a lot of the language modeling work to come from the lab. Ruhai, Taylor, and Andrew have also been working on the LLM stuff, and the rest of the students don't need to hate their lives so much by doing engineering infrastructure work. A ton of references, a lot of information overload. You can pause the YouTube link video once this goes online if you want to go into this. But yeah, thanks for hearing a 7 a.m. man waffle.
Thank you very much, Jason. That was great. And thank you again for getting up at such a horrendously early hour and giving a talk.
No, you're good.
Cool. Yeah, we've got a few questions. I'll just read some of them out, although I know that you're keeping track of as well. But let's start with Thomas's question, which got the most votes here, which is getting rid of spiking early on. And he's asking if that's because you're locked into PyTorch and dense tensors, as opposed to using custom code where you can use sparse operations. And then he says, is there still some room for spiking?
Yeah, okay. So yeah, we did pull away from the purest take on spiking once we had our sights set on state of the art. It's not because of what we're locked into PyTorch. I think it is straightforward enough to write or to pull sparse kernels. If you want them to be leveraged on GPUs, then you need sparsities of greater than like 85% or so, which isn't unmanageable in most layers, but just separate experiments have shown us that the first and final layers of a large-scale LLM, they have a really hard time hitting those sparsity levels. That's not to say that that stops you. Okay, just don't do sparse ops with those specific layers, and you can get away with sparsity in the rest of your model. But really, it's just because GPUs. It's the fact that we're relying on GPUs, not PyTorch. You're providing power to that GPU regardless, right? Let me take a step back. Different people have different metrics that they're optimizing for. If you're in the edge LLM case, then yeah, energy matters, right? Throughput matters. Those numbers matter. If you're a cloud provider of LLMs to many users, TCO cost is all that matters. You want to be able to serve as many users, and those GPUs are powered whether you like it or not. So you sure as shit need to be able to fully utilize every single one of those cores on your GPUs. So as a result of that, the way that GPUs are engineered at the moment makes sparsity really redundant. So it was really a GPU limit rather than a modeling limit. That's not to say that, but that to me is an open opportunity. That's something that we've only explored so much, right? The MatMul-free model, when we deployed it onto Loihi, the sparsity came for free from ternary weights. We did then do some regularization to penalize the absence of sparsity. So that's how we kind of hit 100 tokens per second at the 2 watt regime. But there's no activation sparsity. I personally find activation sparsity really difficult to work with. But difficult to work with is what we researchers need to push for, right?
Yeah. Maybe this gets to Tim Mascalia's follow-up question, which is could you implement it using event-driven processing, at least at inference?
Let me think about that. Man, so language specifically feels difficult for that. If we're defining event-driven processing as skipping time steps and only focusing on the sequence steps where there is something present, then I think language models are inherently quite dense. There's always going to be some neurons active at any given step. But that's not to say you can't take advantage of sparsity. So a couple of students have been looking at the activation sparsity side of things so that you can leverage asynchronous processing on Loihi, et cetera. We haven't released any of those results because, I mean, they work, but they're not impressive enough, to be honest. That could just be an us problem, though.
Okay. Okay, let's move on to the next one. I'll ask this one from Andre, who says, "Is this architecture similar to something like Mamba?"
Totally. Yeah, so Mamba piggybacks off the state space model literature.
Yeah. Okay. All right. And he says also, have you considered implementing more complex state space models by using multi-compartment models or dendrites?
Uh, hmm. So if you look to Gen 3, I am sure that there is an interpretation of those models that could be linked back to multi-compartment models. I don't think anyone has really gone there yet. So low-hanging fruit, perhaps. In terms of dendrites and sequence-based processing and more order, accounting for the order of arrival of events, I have considered the hell out of it. And now that we have a spare moment with the loop language model being released, I think that is a really cool direction to go into. I used to be really skeptical. So when I used to give talks on spiking neural nets, I used to always bring up the 3 S's. I would say spikes, sparsity, static suppression, event-based processing. But the one thing that really was missing there was just the fact that spikes can enable far more compressed and efficient representations of information if you use them right. If you order them, and you can get factorial explosions of what you can possibly represent. That is really worthwhile, and dendrites seem to be a key to enabling that, because you need delays to the dendritic delays or whatever delays you want to be able to encode that kind of thing. So it's just an abstract thought for now.
Yeah,
Call
great.
myself